So the fact that we're in section 5.3.1 and we've understood the fundamental theorem of calculus part 1 leads us to ask the question, why are we here? Why in the world again do we care about taking derivatives of weird functions that have or that look like definite integrals? Why? And what in the world does this have to do with the rest of Chapter 5, which remember so far has been concerned with calculating definite integrals, finding areas under curves. So as I state up here, while we see how this theorem can be used, we may still question, why is it significant? What relevance does it have to the idea of calculating definite integrals? So let's consider one of the following implications of part 1 of the fundamental theorem. Let's take a look at what we have. Let's suppose again we have one of these integral function things, and we know that from the fundamental theorem of calculus, as long as x is in the interval from a to b, the derivative of this function is going to be f of x. Well, now I'm going to pull on some knowledge that we learned about near the end of chapter 4, which is that I know some stuff here about antiderivatives. So if it's the case that the derivative of g is equal to little f, then I should be able to say that regular g could also be expressed as capital F of x, the antiderivative, of course just plus c. So this is again where capital F of x is any antiderivative of little f of x, and c is some constant. So what's kind of interesting now is that we have actually here two different ways of representing the function of g. We can represent it with this big crazy integral thing, but we can also represent it with this antiderivative, capital F of x. So apparently both of these things, the crazy definite integral and the capital F of x plus c, should be the same. So I know actually then they should also be the same whenever I'm using values in the interval from a to b. Now again, I should see here that since f of x had to be continuous for this derivative rule to work, and that means that my derivative is defined, and that means that my function g is differentiable and therefore continuous, I can state then the following. I can say that since little f of x and capital F of x are going to end up continuous, I can say that we know that the equation of g of x equals capital F of x plus c is true for all values of x in the interval from a to b. So again, I know for sure that this formula here and this formula here are really ultimately saying the same thing. Well, now let's take a look at some implications of this. Let's take a look at the following. What if I say that I went to this function of g of x and I plugged in, say, the value of a, right? Let's just suppose that I did this and I wanted to see what happens. Well, I could definitely see that g of a would be equivalent to going to my function here and replacing x with the value of a. So that would give me a to a of f of integral from a to a of f of t dt. And of course, I know by my integration properties that this is just going to actually be 0, right? I've grabbed no area underneath f of t. But now I should ultimately see that, well, wait a minute. This is the answer that I got for this representation of g, but then I should get the same answer when I go ahead and I plug in a into my other representation, which of course would look like this. So this implies, and I guess I left that word out here, but this implies that this here is going to be equal to 0 on that side. And so I can go from here and make the claim that the value of c is actually equal to negative f of a. So this is kind of a weird point. Again, all we're highlighting is that if g of a or g of x is equal to this representation and this representation, then they should produce the same values. So if this thing produces 0, then this thing should produce 0. Easy peasy. Well, now let's go ahead and take a look at what would happen if I was to plug in the value of b in place of x. All right, well, this is a little less interesting in the first representation, right? Because here I'm now going to get an integral from a to b of f of t dt, and I can't really say what in the world that's going to be equal to. But I know that this is going to imply the following. So this is going to imply that the answer that I get when I plug in the value of b in here should produce the same result that I had over there. So notice here I'm going to get f of b plus c. But I know that c, from what I saw up there, is actually just going to be the same thing as negative f of a, or I could just rewrite that as f of b minus f of a. And again, since g of b equals this, and g of b equals this, these two representations have to be equal to each other. So, for any continuous function f with an antiderivative of capital F, we can say, by what we've shown here, that this integral from a to b of f of t dt is going to be equal to, well, whatever this spat out, which was f of b minus f of a, where capital F, again, remember, is an antiderivative of the original function. Now, I'm going to end the argument here, and if we really have understood what we've said here, our jaw should be on the floor. This is incredible. Notice that we've said as long as I have a continuous function on the interval from a to b, and I can find an antiderivative of that function, call it capital F, then to find the area under the curve, all I have to do is take f of b, that is f of the upper limit, minus f of the lower limit, and I have the area. This is what we summarize as the fundamental theorem of calculus part 2, and it is way better than part 1 because it shows us that for any function at all that I'm trying to find the area under, I just need to be able to find an antiderivative of that function, and I can immediately calculate the area. So again, I'm going to see here that this capital F here is any antiderivative of our little f. This is amazing. This is going to be the theorem that is going to allow us to be free from evaluating really, really difficult sums like we saw back in some of the earlier sections. To find the area under the curve now, I can see this incredible, surprising link that really all I need is to understand antiderivatives. If I can find that my function is continuous and I can find an antiderivative of it, I have this unbelievable shortcut for calculating the area under the curve. And we'll see how this applies in many of the examples that remain in this section.